I want to start by asking you to imagine that you're an astronomer and you're based at an institution like this, and I'm not sure if you can see on the slides, but there's a shape across the night sky coming from the left to the right, which is the trajectory of a satellite that you're observing. And I want you to imagine that you're trying to either predict the trajectory of that satellite or explain why it has the trajectory that it does. How would you go about doing such a theoretical process? One way, probably the most familiar way to anyone who's thought about questions like this before, would be to construct a model of the situation. One way that you would go about constructing such a model is you would assume that the Earth is a fixed, perfect sphere. The satellite is some point mass which is significantly far from the sphere, and you'd calculate the gravitational potential that's acting on the satellite as a result of the spherical body, the Earth. Gravitational potential would look something like this, and then from the potential you can solve for the acceleration of the point particle, combine that with some observations, the initial conditions of the satellite, and this would suffice to explain or predict the satellite's trajectory. But when you've done this sort of theoretical work, you've constructed a model that differs from the actual system in some fairly significant ways. So in your model, there are no other bodies other than the Earth and the satellite. In the target system, there are clearly other bodies, right? There's the sun, there's the moon, there's a bunch of other satellites, a bunch of other planets, and so on. In your model, you've assumed that the large body, the thing that represents the Earth, that's fixed according to some reference frame. But in actuality, the Earth moves. The Earth itself is orbiting around the sun as well. Most importantly for today, in the model, you've assumed that the Earth is a perfect sphere. But in actuality, it's not so perfect. There are mountains, and it's actually an ellipsoid. Again, in the model, the satellite is a point. It's a point particle. Any actual satellite will be extended. And also, gravity in the model you've assumed to be Newtonian, and that's actually not the case in the target system for complications about general relativity or quantum gravity. So there are plenty of important differences between the situation that you constructed in the model and the situation that you're trying to explain, the actual trajectory of the satellite. But nevertheless, despite these differences, or despite these inaccuracies, we take it, or we hope, that the model is still explanatory. It still allows you to explain why the satellite has the trajectory that it does. The task that I want to talk about today is, can we explain why the model is explanatory in the way that it is? Why is it that those model target divergences don't undermine the explanatory capabilities or the explanatory power of your scientific model? Okay, so the plan for today. I'm going to start by talking about the relationship between accuracy, truth, veridicality, and explanation. I'm then going to talk about a particular sort of philosophical debate about how to understand the structure of some particular types of explanation, what I'm going to call universality explanation. Here I'm going to draw on some contemporary philosophy of science, and I'm going to argue that our current best philosophical understanding about how these sorts of explanations work, this philosophical understanding which is supposed to weaken that connection between accuracy and explanation, actually will just amount to being a version of a more traditional accuracy-based account of how idealization works. And in the final section of the talk, I'm going to explore the extent to which we can think about this structure of how idealized explanations work, the extent to which this is actually fairly generic. And here I'm going to talk you through an example, and I'm going to ask, I guess, of you how this structure that I'm going to identify for how such an explanation will work, whether or not that features in the sorts of explanations, scientific or otherwise, that you yourself work with. I want to offer a caveat here as well. As I'm going to present it, this talk is fairly inside baseball. There's a sense in which I'm, or we, I should mention, by the way, that this is based on joint work with Nick and Patrick. There's a sense in which what we're doing here is intervening on a very particular contemporary philosophical debate, and this is the way that I'm structuring the talk today as well. So for that, I apologize. But it is worth noting that in our intervention, the thing that we are trying to highlight is something that should be of much broader philosophical importance or philosophical interest. The question is the extent to which the structure that we're going to outline about how such explanations work is in fact relatively generic across the sciences and maybe more generally too. Okay, so to get started with a sort of recap on why you might think that the notion of explanation and the notion of accuracy are intimately related to one another. So this is a sort of standard philosophy of science 101 example. And you ask students to offer an explanation of why, when that figure skater pulls their arms in, why his rotational velocity increases. Why does the figure skater speed up when he brings his arms in? And the answer that we usually want is something like, well, because angular momentum is conserved, and when a rotating object's radius decreases, its angular velocity must increase. So the conservation of angular momentum, combined with the fact that when the figure skater brings their arms in, their radius decreases, therefore the angular velocity must increase. That's the sort of explanation that we usually want when we're trying to explain this example in Philosophy of Science 101, or indeed in Physics 101. Versus, suppose I said, how do you explain why the figure skater sped up when he brought his arms in? And you gave me an answer, something like, because some little gremlins get excited and spin the skater with more vigor when the skater brings their arms in. What is it about that first explanation, that first answer to the question, which seems explanatory, and the second answer to the question seems non-explanatory, or seems wanting in some important respect? I take it that one of the answers that you'd be inclined to give there is because the first explanation is true, or the first explanation is accurate. It is the case that angular momentum is conserved, at least for closed systems. It's not the case that gremlins get excited when figure skaters bring their arms in and spin people around on their figure skate with more vigor. You can't read this, but this is just to give you some, I guess, history of philosophy of science. So in the mid-20th century, the sort of first discussion of how explanation worked in the philosophy of science goes back to Hempel and Oppenheim, and they suggested something that's called the HD model of, the DN model of scientific explanation. According to the deductive nomological model, in order to explain some phenomena in the world, you do so by offering a deductive argument. The deductive argument has to be valid in the way that logicians talk about it. It has to involve at least one law of nature, or law-like statement, and all of these statements that are in the premises of that argument have to be empirically testable. In addition, on this final section here, which again I'm not sure that you can read, there is this condition of adequacy, which is that the sentences that constitute the explanation, or the explanans, they have to be true. So just to give you a little example, just to go over our previous example in the mode of the deductive nomological account, an explanation of why the figure skater speeds up when he brings his arms in is given by something like the following. We have a law-like premise, angular momentum, in this case the product of moment of inertia and angular velocity of a closed system is conserved. The skater is a closed system. The skater's radius decreases, which reduces his moment of inertia. If you have angular momentum being conserved, which is the product of two values, one of which goes down, the other of which has to go up, and that deductively explains why when the figure skater brings their arm in, decreases their radius, they'll increase their angular velocity. Compare this to a deductive argument of the following form. Gremlin excitement is inversely proportional to the radius of the objects to which they're attached. Gremlin excitement is proportional to velocity. The skater's radius decreases, which increases the Gremlin excitement. Therefore, the skater's angular velocity increases. So we've got two deductive arguments, both of which are leading to the conclusion that we're trying to explain, the angular velocity of the skater increasing. What is it that distinguishes between these two arguments? Well, it's not captured by the law-likeness of any of the premises. So in the first case, we have angular momentum being conserved. In the second case, we have some general law-like claim about how gremlins get excited. So the law-likeness is equal in both. Whoops. It's not captured by the deductive validity of the arguments. Both of those arguments are equally valid. And it's not captured by the empirical testability of the premises involved either. I can't go about testing these premises. They're not the sort of things that are supposed to be beyond the realm of observation. So rather, what captures why that first explanation is explanatory and the second explanation is not, is the fact that the first explanation has true or veridical premises. There's a more modern account of explanation, which also builds truth in as a necessary condition of explanation. And this is developed by Michael Strabins. There's a picture of him here at the bottom of the slide. And the idea, according to Strabins, is that to understand or to explain a phenomena is to see what made a difference to its causal production and how it did so. At the heart of the queretic, I don't know how to pronounce that word, account of explanation then is a criterion of difference making. So here I'm just going to spell out the details of Strabins' account because it's going to be important when we come to apply it later on. So the basic idea, according to Strabins, of how we go about explaining some phenomena in the world is to start with some veridical description of the causal chain that leads up to that phenomenon. We assume that that veridical description of the causal chain that leads up to that phenomena can be put in the form of a deductive argument that entails the explanandum. So we're going to call this the veridical model. And then we're going to do this process of optimizing the veridical model in such a way that we either remove or replace with more abstract counterparts statements of the model in such a way that the derivation of the explanation remains. I'm going to call this the canonical model. This all sounds quite abstract. Let's just see it in action with a toy example. So suppose that what you're trying to explain is why the window broke. Your explanation for why the window broke, it starts with this veridical model, this specification of the causal chain that led up to the breaking of the window. So in this example, we can think that the causal chain that led up to the breaking of the window, something like there's a cannonball with a mass of 907 grams, and it has such and such a precise trajectory that leads it to collide with the window. There's some general law, much like the deductive nomological account, where when cannonballs hit windows, they cause them to break. Therefore, from 1 and 2, we infer that the window will break. But there's a sense in which that first premise is specified in too fine-grained a level of detail for the explanation that you want to give. You're trying to explain why the window broke, and that first premise is specifying the precise weight and the precise trajectory of the cannonball. So Strabins says, well, we should do this optimization process where we move from this very precise specification of the causal chain that led up to the event to be explained to some more abstract specification of the causal chain that led up to the event to be explained. In this case, we notice that it doesn't matter. The exact weight of the cannonball doesn't matter. It doesn't have to weigh 907 grams in order for the cannonball to break the window when it hits it. And the exact trajectory of the cannonball doesn't matter. It doesn't matter that it flowed through these positions in space. All that matters is just that the cannonball and the window collided with one another. So we abstract away the content of that first premise until we get to something like a cannonball with some mass which is greater than 1 gram hits, according to some trajectory, a window. When cannonballs hit windows, they cause them to break. Therefore, the window breaks. So the central idea, according to this way of thinking about scientific explanation, is that we can start with some arbitrarily fine-grained veridical causal causal model of the event to be explained, and we subject it to this optimization procedure. This optimization procedure which removes detail that is unnecessary for in order to derive the explanandum. We remove the fact that the cannonball has some particular mass, 907 grams, and we just say the cannonball had some mass that was greater than 1. We remove the fact that the cannonball took this particular trajectory, and we just replace it with the fact that it had some trajectory which caused it to coincide with the window. Once we've done that, we've specified the explanation at the appropriate level of grain, given the explanandum to be explained, and that's what amounts to a scientific explanation, according to Strevens. Now, it's important then that one thing that's built into this way of thinking about explanation is that the models in question, particularly that veridical model, but also the canonical model, they have to be true. They have to be veridical. And in order to understand why that's the case, let's go back to our gremlins. Suppose I offered a canonical explanation of the form, the cannonball carrying the gremlins comes close to the window. When gremlins come close to windows, they smash them, therefore the window breaks. This one seems to be stated at the appropriate level of abstraction, given the explanandum to be explained. It's also a deductive argument. That deductive argument is supposed to track the causal process, but nevertheless, there's something wanting about that. So according to Strevens, that veridical model and the canonical model that is constructed from it, they have to be true. They have to be veridical. There are many other accounts of explanation that I could offer here, but most of them, at least, have built in as a necessary condition on providing a satisfactory scientific explanation that you have accuracy, that you have veridicality. And I think the reason why they have that is precisely to rule out the sort of silly examples that I've given you about gremlins causing people to spin faster, or causing people to, or smashing windows when they go along with cannonballs. So there's a clear sense in which this idea of accuracy, of veridicality, is being built in to our account of scientific explanation precisely in order to rule out those sorts of silly examples. Okay, so what about universality explanations? So the way, at least, that it's understood in the contemporary literature goes back to these two philosophers here, Bob Batterman and Colin Rice. And what they argue is that there's a class of explanatory models whose explanatory structure has been almost universally misunderstood by philosophers like Hempel with the deductive nomological account, or like Strevens with his quadratic account of explanation. And according to Batterman and Rice, what makes these type of explanatory models special is that they're used to explain patterns of macroscopic behavior across systems that are heterogeneous at smaller scales. So I'm going to give you an example that they use of a universality explanation. So on the left, it's left for you too. On the left is a model, is the lattice gas automaton, and it's specified as is kind of depicted in this image here. So you start with this hexagonal lattice, and you have a bunch of particles that are constrained to the vertices of that lattice. Those particles have a direction, and they have some sort of velocity, and there's an update rule on the automata. The update rule says if you have two particles coming to the same node on the lattice, then they'll bounce out at a particular angle. Otherwise, the particle will just flow through that node in the lattice. You can run this model, it's got a discrete time structure, so you can just update in discrete steps the behavior of this model. And the claim that Batterman and Rice make is that we can use this lattice gas automaton, or automata, to explain actual worldly behavior of fluids. For example, to explain the particular profile of a fluid as it moves across a plate. So you see the plate on the left of this image. You're interested in trying to explain why, as water flowed through a pipe with a particular blockage, it has the momentum profile that it does. One way that you construct such an explanation is by constructing the lattice gas automaton. updating it in this particular way, maybe running it multiple times and averaging across the results, you get something like what's displayed on the right-hand side, which is supposed to be a good explanation of why the water behaves the way it does when it flows through a pipe. But built into this lattice gas automata are all sorts of distinctions, differences, inaccuracies between the model, the thing that's doing the explaining, and the target system, the thing that you're actually trying to explain. For example, the model's set on a 2D hexagonal grid. It's pretty obvious that water in a pipe isn't set on a 2D hexagonal grid. These dynamics are extremely simple. It's just to do with this update rule, whether or not two particles hitting at a node are going to bounce out from one another or they're going to flow through. Time is discrete. You have this very much, update one time step, one time step, one time step. All of these are not features that are present in the actual liquid that flows through the pipe. All of this, you might think, makes the model inaccurate in those respects. But it is worth noting that there are some respects in which that model does agree with the behavior of the water as it flows through a pipe. For example, particles are only influenced by what's going on in their immediate neighborhood. The total number of particles and the total momentum of the system is conserved, and the system is isotropic and rotationally invariant. So the fact that there are some of these inaccuracies, some of these model target divergences, doesn't prevent the fact that there are some similarities between the two systems. What Batman and Rice argue then is the way that this model works is it allows us to answer a particular set of explanatory questions. So it allows us to provide our explanandum. It explains why when fluid flows past a plate it has the profile that it does. But also, more importantly, perhaps, the model allows you to answer questions like why these similarities, these locality, conservation, or symmetry, why they're necessary for the phenomena to occur, and also why those dissimilarities, the ways that the model and the target diverge with respect to one another in very seemingly significant ways, why that's actually irrelevant to the behavior that you're trying to explain. So the model doesn't just work to explain why the water flows through the pipe in the way that it does. The model also works to explain why it doesn't matter whether water has the particular, the particular distribution of particles with the particular trajectories that they have. It could just as well have been a load of small individual particles constrained to a hexagonal lattice. So not only do you explain why the phenomena happens the way that it does, you also explain why it doesn't depend on the particular details of the microscopic constituents of water. And this allows you to explain why very different fluids exhibit these features and have the similar sort of fluid flow behavior. Here's a diagram which I'm going to draw on quite a lot when I start talking about the ubiquity of this. So it's worth spelling out the details of what's going on here. So on the sort of lower aspect of the diagram, what Batman and Rice urge us to the way that Batman and Rice urge us to consider how these sorts of explanations work is that we have this class of different systems with different underlying microdynamics. So at one point in this lower diagram, the one that's labeled LGA, that's the lattice gas automata. At some other point in the diagram, it doesn't matter which one, but let's say the one on the far right there, Fi, that's supposed, for the sake of illustration, that's supposed to be the actual system, the actual setup with the microscopic particles that we'd have in an actual flow of water through a plate. The way that Batman and Rice argue that this sort of explanation works then is that we need to find some sort of procedure for abstracting away from the details of the microscopic dynamics. This procedure is the thing which is giving us these dotted lines, where the idea is that if we apply this procedure to the lattice gas automata and we apply this procedure to Fi on the far right-hand side there, at some point they're going to coincide. At some point, once you look at both of those systems at the appropriate sort of coarse level of grain, they're going to look like the same system. In contrast then, you could imagine some other system, in this case it's the F plus on the left-hand side in the middle. That's something which doesn't have the appropriate locality conditions or doesn't have the appropriate symmetry properties. And if you apply the procedure to that, you're going to get some other type of macroscopic system. So you have this bunch of different systems in the bottom half of the diagram, such that once you abstract away from the details of the microscopic dynamics of those systems, they're going to coincide on this point, in this case labeled P plus, in the higher edge of the space. So the idea is that in order for these universality explanations to work, you need something like the following setup. You need some space of possible systems, the lattice gas automata, some other automata based on different shaped lattices, some actual system based on water flowing through the fluid pipe, some other system based on some other liquid thrown through a pipe, or water but with slightly different underlying number of particles, for example. So you have this bunch of space of possible systems. You have some method for coarse graining each element in that system. You have attractors in the space. I'll talk more about that when we get to the genericity of this. And the idea is that we have some way of being able to describe how across this diversity of microscopic systems, all of them nevertheless, under this coarse graining procedure, flow to the same point. When you have that system, when you have that setup, which in this case we're assuming that we do with respect to the lattice gas automata on the one hand and the actual water flowing through the paper in the other, when they flow to the same attractor, the hope is that we can use the model to explain, for example, why the target behaves the way that it does, why that behavior depends on features that all elements of that universality class have, and crucially, why that behavior is independent of the features that vary across the universality class. So if you can show that the lattice gas automata, if you can show that the lattice gas model and the veridical model, the actual specification of the underlying microdynamics of water as it flows through a pipe, if you can show that they flow to the same space, the same point in this abstract space, then you can explain why the behavior, e.g. the fluid flow, the momentum profile as the water flows through the pipe, why that behavior is independent of the fact that, for example, the lattice gas automata is set on a hexagonal grid, whereas an actual water flowing through a pipe is set in three-dimensional space with particular trajectories of the underlying particles. Okay. So I essentially agree with Batman and Rice's way of picking out the structure of those sorts of explanations. But where I disagree, or where we disagree, is with respect to the moral that they draw from examples of this kind. So according to Batman and Rice, they argue that the fact that these universality explanations are taken to be explanatory in scientific practice suggests that we've actually failed to realize that there are two ways, or at least two ways, of justifying how an idealized explanatory model explains. So according to one way, according to Batman and Rice, of justifying how an idealized model explains, is it accurately represents the difference makers of the phenomena. So they would say, I think, of an example like the angular momentum case, that the reason why that's explanatory is because it accurately represents those difference makers. The moral that they draw from the use of universality classes or universality explanations is that there is another way of justifying how an explanatory model works. And that other way of justifying it is based on that structure of a universality explanation that I offered above. So they very much sharply distinguish between explanations that work by accurate representation of difference makers and explanations that work in some other way, this universality way. In this case, that they conclude that the lattice gas model explains why when the liquid flows through the pipe it has the profile that it does, despite the fact that it's an inaccurate representation, and therefore that they conclude accuracy is not necessary for something to be a good explanation. Okay. So I gave a quote from Strevens above, which is bolded here. No causal account of explanation, certainly not his keratic account, allows for non-veridical models to explain. But it's worth noting that that quote is embedded within a broader discussion. And the broader discussion is as follows. An idealized explanatory causal model misrepresents elements of the causal model that produces the explanatory target. It will be difficult then for the causalist to explain why idealization is so common. So Strevens takes it on himself to explain or to offer an account of how idealized models, models which are inaccurate representations of the causal processes involved, how they can be explanatory. So now I'm just going to spell out what Strevens says about idealization. So just in order to put things in context, what you should have so far is sort of straightforward Strevens account of how explanation works in cases where you don't have idealization. A Batterman and Rice account of how explanation works where you have one, idealization, and two, this notion of universality classes in the background. And now I'm going to present to you this third aspect, which is what someone like Strevens, or an accurate representation of difference makers person, would say about idealization. So recall, according to this sort of Strevens account, you have this move from what I call the veridical model. So this is the specific description of the causal chain that leads up to the thing to be explained. It's the particular mass of the cannonball, the particular trajectory it takes. And you have this optimization procedure where you abstract away features that don't make a difference. So you abstract away the precise value of the ball's mass. You replace it with a claim like the ball has a mass of at least 1 gram. You abstract away the details of the trajectory and you replace it with something like the ball hits the window. According to Strevens, then, the way that we should think about idealized models, cases where you don't start with the truth, should follow a pretty similar procedure. So in this case, the example that he gives is the ideal gas law, where, for example, you assume in the model that the long-range intermolecular forces between the particles in the gas are 0. So you start off with your idealized model, which is a specific description, just like the cannonball model was a specific description. But in this case, because you're talking about idealization, some of those elements of that description are false. For example, in the model, you might assume that long-range intermolecular forces are 0. But nevertheless, just because you have those falsehoods in the model, that doesn't mean that if you subjected it to the optimization procedure, that those falsehoods would be retained. So, for example, if you took your idealized model, where you assume that long-range intermolecular forces were 0, you applied the optimization procedure, what you would get is your canonical model, where it specifies a range of those falsehoods. It specifies a range of the force values for long-range intermolecular forces. 0 is within the range. Your false assumption, your idealization assumption is within the range, but so is the true thing. The true thing is also within the range. Intermolecular forces are low enough that they don't make a difference to the phenomenon. So you can start with your idealized model, which is pointed again. It's a fine-grained description, but a fine-grained description which is false. You can remove detail from your idealized model, and you can arrive at your canonical model, which is not fine-grained anymore. It specifies things in terms of ranges, and where those ranges are true of the target to be explained. And then Strevens claims then that an idealizing explanation, or an idealized model, is always better than its veridical counterpart. In this case, it's always better than the actual fine-grained description that you would give. It's always better than the analog of the cannonball having the mass of 907 grams. And also, in one important sense, it's at least as good as the corresponding canonical model that you could give, the coarse-grained description which is true. Just to explain why he thinks these two things. And the first thing to note is that the idealized model is at least no worse than the veridical counterpart. They both imply the canonical model. What do I mean by that? So your idealized model of, for example, the ideal gas law, where you assume long-range intermolecular forces are 0, when you subject it to the optimization procedure, you get a claim like the long-range intermolecular forces are small within some certain bound. It's also the case that the veridical model, the exact specification of the trajectories of the molecules in of the exact specification of the long-range intermolecular forces in a natural gas, also, when you subject it to the optimization procedure, will say long-range intermolecular forces are low and within some certain bound. So in a sense, the overly specific, overly fine-grained vertical model the idealized model is just as good as the overly specific vertical model, precisely because they both imply the same canonical model. Once you do the abstraction, you get to the same result. But moreover, there's something wrong about the vertical model, at least as it comes to the explanation that you're trying to give, because when it specifies the exact value of long-range intermolecular forces, or it specifies the exact trajectories that those particles, those molecules take, it mistakenly suggests that they're difference makers. In contrast, the idealized model, the thing that sets that to zero, that identifies them as non-difference makers, but it does so by misrepresenting them. So again, maybe that was slightly fast, so go back to the cannonball example. So in the cannonball example, I said that you start with your fine-grained explanation of the causal chain that leads up to the window breaking. That's not explanatory ideal. That's not an explanatory ideal. There's something wrong with that explanation. What's wrong with that explanation is that it seems to suggest that 907 grams, or some particular trajectory, that makes a difference to the window breaking. It's only by doing the optimization procedure, by abstracting away from those details, that you reach something which is explanatory optimal. So in a case where you have this idealized case, the vertical model, the thing that specifies all the fine-grained details, that's also not explanatorily optimal. It, for example, is specifying things that don't make a difference, like the long-range intermolecular forces. And in that sense, it's worse than your idealized model, which correctly represents long-range intermolecular forces as not making a difference, but it does so via this unverticality, via this inaccuracy. So it says they don't make a difference, and it does so by setting it to zero, which is something that we know that is actually false. Okay. So now, in which case, compare your idealized explanation, the case where you have the misrepresentation, where you set long-range intermolecular forces to zero, with your canonical explanation, which says long-range intermolecular forces are within this particular range. The idealized explanation is at least as good as the canonical model, insofar as they both accurately represent the things that make a difference. They both accurately represent the things that make a difference, and they effectively communicate the things that don't make a difference. It's just that the way that the idealized model communicates the things that don't make a difference is by idealizing, is by setting them to zero. Okay. What we claim then, or what we want to claim, is that this way of accounting for idealization within the context of an account of explanation that requires accuracy is structurally identical to what Batman and Rice call a universality explanation, to the example that I gave above of the Lattice Gas Automata. And what we want to identify in trying to make this claim is something like the following. So when Strevens is talking about canonical models, when Strevens is talking about abstracting away from the fine-grained detail that don't make a difference, what he's effectively doing is specifying a space of systems. So the example that we gave previously was this idea that you could have this cannonball where you have some particular value for the cannonball's mass, and the way that you construct the canonical model is by specifying some range in which the mass could have, as long as it was in that range, it would still break the window. So that canonical model then contains a collection of systems where the cannonball has a mass 907, one where it has a mass of 906, one where it has a mass of 3, so on and so forth. You have this space of possible systems with cannonballs with different masses. You have a veridical model, which is some model in that space that is supposed to accurately, to an arbitrarily fine-grained level of detail, represent the actual causal chain that led up to the behavior to be explained. And you have an idealized model, which is some other point in the class where its fine-grained details are false, e.g. it sets in long-range intermolecular forces to be 0. And you have some sort of flow in the Batman and Rice case. They're drawing on the machinery of the renormalization group. We'll talk about that in a second. And you have some sort of optimization procedure in the Strevens case, where you're abstracting away from the details. But the result is going to be that you take all of these different fine-grained systems with different fine-grained details. Once you optimize, once you abstract away, you get some agreement at a coarse-grained level, and that's what allows you to do the explanatory job. Okay. So far, I want you to keep in mind, I guess, the two following claims. So the first claim is that you might think, if you follow Batman and Rice, that there's something special going on about universality explanations. They work in some sense in an importantly different manner to the accurate representation accounts of how explanation works. In contrast, you have this discussion, this more nuanced discussion about how accurate representation of difference makers, how that works, where crucially it involves this abstraction. It's the idea that you can constrain yourself to accurately represent difference makers without thereby committing yourself to the idea that you provide some arbitrarily fine-grained accurate representation of the micro details. The other thing that I want you to bear in mind then is something like this picture, where you have this space of possible systems, you have your arbitrarily accurate veridical model of the target to be explained, you have some idealized model, which is some other point in the class, and you have some sort of procedure for ensuring that those two models will flow to the same point under a certain coarsening. Okay, so now we want to talk about whether or not this procedure is ubiquitous, the extent to which we can think about maybe all, maybe not all, many paradigmatic instances of explanation as taking this sort of structure. So again, let's go back to the example of trying to predict or trying to explain the trajectory of the satellite across the night sky. So you recall the way that I set it up is that you construct a model where you assume that the Earth is a fixed perfect sphere, the satellite is a point mass which is significantly far from the sphere, and you calculate the gravitational potential of the system. Once you've done that, you can solve for acceleration. Once you combine some initial conditions into that, you can solve for the trajectory. Like I said, like I spell out here. And then the way that we've set this up then is that, or the way that we're sort of problematizing this, is that when you've provided this explanation, or you've provided this prediction, you've made a bunch of idealization assumptions. You've assumed that there's no other bodies in the system, you've assumed that the large body is fixed, you've assumed that the small body is a point, and so on and so forth. So we're going to focus just on one particular idealization assumption here, with the claim that this process would be analogous if we were to focus on any of the others too. So let's focus specifically on this idealization assumption that the large body in the model is a perfect sphere, where the Earth, the actual thing that we're trying to explain, the orbit of the satellite around the Earth, the actual Earth is an irregular ellipsoid. So the details of the mathematics here aren't too important and are also probably beyond me, and I'm very grateful to Philip and Nick for trying to explain this to me the best that I can. What I want to offer here is just really just about the shape of what's going on in this sort of example. So when I said before that you construct your model and you try and specify the gravitational potential, this is the equation that gives you the gravitational potential of the idealized model, of the case where you assume that the Earth is a perfect sphere and you have the point particle orbiting around it. Patrick and Nick assure me that we don't have to do that. As our modeling assumption. We have the resources to specify a model which more accurately represents the shape of the Earth. The resources that we have are given by this sum on the right-hand side here, where I guess the idea is that each element of this sum corresponds to what's called a multipole moment, and the actual total sum, as you put more and more detail in about the shape of the Earth, you can look further down this sum to capture that detail. So we start with the idea that the Earth is a perfect sphere, and in which case we can just ignore that right-hand term. Alternatively, if we want to represent the fact that the Earth has a particular ellipsoid shape, then we have to include more elements of the term. If we want to represent the fact that it has an ellipsoid shape and it has mountains on it, then we have to include more elements of the term, and so on and so forth. But the point to make, if you're trying to explain something like the trajectory that you observe from that astronomy tower, from that thing on the top of Haleakala in Hawaii, say, you're not trying to explain the exact trajectory of that satellite. In particular, you don't even have access to that exact trajectory, right? Any way that you go about measuring the behavior of that satellite is going to be, in some sense, require that what you're explaining is within a range. You can't explain the pointed trajectory. So, following that Strevens discussion, if you were to take the full expansion, you would be in the analogous situation to having specifying the exact trajectory and mass of the cannonball. You're doing something that's too precise for what it is that you're trying to explain. So, if you follow this Strevens procedure, what you're actually going to be doing when you're trying to find your canonical model, the model that's stated at the appropriate level of coarseness, is you're going to try and find something like this, where you realize that you may have to include some range for the effect that the further multiple moments make. But the details of that don't matter. As long as that value is small, it's in a range which includes 0 but isn't exhausted by 0. As long as the range is small, then you'll be able to explain the phenomena, the satellite traveling the way that it does, at the appropriate level of grain that you want to explain the satellite's trajectory. Remember, you don't want to explain the precise trajectory. You don't have access to it. What you want to explain is why it has this particular shape that it does. The claim, then, is that this example exactly marries or exactly matches Strevens's discussion. You have your idealized model, where the Earth is a perfect sphere, and the gravitational potential is given by the equation at the above. You have the vertical model, which includes all of the details about the shape of the Earth, and is given by this full multipole expansion that's given to the bottom. But once you realize that what you're trying to explain isn't the precise trajectory, you're trying to explain the shape of the trajectory, you have this agreement of the idealized model and the vertical model under the coarse graining procedure on the bottom. And it just looks like that, right? So you know that if x took the value 0, you'd have your idealized model. If you take your vertical model, you need that sum on the right-hand side to take some small value between 0 and some lower bound, upper bound. So the claim, then, is that this, if I'm right, or if we're right, you're able to explain this example of the multipole expansion using Strevens's setup. Also, we claim that Strevens's setup is just exactly the same as Batman and Rice's setup. The implication of those two claims would just be that this multipole expansion also takes the form of a universality explanation. And remember that quote from Batman and Rice previously, the idea being that we have two different ways of explaining, of justifying how explanations work. They either work by accurately representing difference makers, or they work via universality. What we're showing here is that maybe all explanations work via this universality claim. It depends on your inclinations here. Are we showing that this is are we showing that universality explanation is boring in the sense that it's generic, or are we showing that it's super exciting? We should have realized that this is what's going on in all cases of explanation. Cases where we thought what we were doing was accurately representing difference makers. What we were doing is we were doing so precisely via following this universality structure. So the claim then is that as applied to the multipole expansion, you have your canonical model, which is a space of orbiting systems where that central body has various different shapes. Within that space of ordering systems, within that space of systems, there is one, which is the veridical model, which takes all of the Earth's actual multipole values. So the Earth, with all its fine-grained detail, with all its ellipsoidness, its mountains and so on, that's within that class. But there's also, within that class, is this idealized model, the model where the Earth is a perfect sphere. The notion of flow, then, is given in this case just by truncating that sum on the right-hand side of the multipole expansion. The more of those terms that you have to pay attention to, the more fine-grained you get, but in contrast, the less of those terms that you pay attention to, you have this flow to a fixed point. Okay, so in the interest of time, I'll skip going through that, but the moral is that the idealized model in this case, the case where you've assumed that the Earth is a perfect sphere, it works to explain, even though it looks like it's inaccurate when you consider it in isolation, but the way that you should be thinking about it appropriately is in the context of that theoretical background where you have the multipole expansion, and you know that those higher order moments, the more fine-grained that you would specify the shape of the Earth, they won't make a difference to the thing that we're trying to explain, at least where the thing that we're trying to explain is such that it's sensitive to how accurately we can, for example, measure it. Of course, if you wanted to explain the precise trajectory of the satellite, this wouldn't work, right? Because you wouldn't do this abstraction procedure. This only works because what you're trying to explain is not the precise trajectory, you're trying to explain it up to a certain level of grain. Okay, in the interest of time then, claim we should think about other instances of explanatory idealization in the same manner, and discussion, this is where I want to ask you, to what extent is this style of explanation generic? So what we need in order for this style of explanation to get off the ground is this space of possible systems, which includes your idealized model. You need to have reason to believe that the target, or at least the more veridical way of representing that system, also lives within that space. You have an explanandum which has some generality. You're not trying to explain the specific details, you're just trying to explain it up to a level of grain. And you've got reason to believe that under this coarsening procedure, this idea of abstracting away the details, the idealized model and the veridical model will flow to the same point. There is one thing that's worth noting here, is that in the cases that Batman and Rice are talking about, you have this explicit mathematical machinery to talk about the flow on the space. In the case that we're talking about, in a sense, you also have this mathematical machinery. It's just specified in terms of truncating the expansion. In the more generic question, the one that I want to ask you, if this is something that seems familiar when I put it in these terms, to what extent should you think about this, how should we think about this coarse graining procedure? Is it something that needs to have a sound mathematical backing, or is it something that is part of scientific practice when it comes to realizing that your models only need to go up to a certain level of detail? Is it just a good sense thing, or is it something that needs to be explicitly represented in the way that the explanation works? And I'll finish there.